this brings us to the first Spotlight Talk session. As we said, it's going to be the 5-minute pre-recorded video and then a 1-minute Q&A. So type your questions again in the Zoom Q&A or in the Slido. I should now have added most Spotlight talkers. I think we are missing Satoshi Funabashi. If you are in the attendance, you can raise your hand and I can add you, so you can also answer questions. Not, it's just going to be the video, so that's also fine. Then, yeah, Martina, you can start the video.
Okay, it's here. I will make it him panelist.
Ah, perfect.
Okay, nice.
And we have everyone.
Okay.
Hello everyone, I'm Satoshi Funabashi from Waseda University, Japan. I would like to talk about our research in hand manipulation of multi-fingered hand with daily objects based on graph convolutional network and 3-axis tactile sensing. In the background, the multi-fingered robot hand is capable of dexterous manipulation. On the other hand, the acquisition of tactile information for the contact states can improve the manipulation stability. So when we see the previous research on multi-fingered hand control, some studies achieved the dexterous manipulation by using deep learning, but there is little tactile info like this one. This research doesn't use tactile information, or this one use only for fingertips. So the achieved manipulation is limited, or the object was specific for the manipulation. On the other hand, when we see the other research which focus on using tactile information for the multi-fingered hand, which is actually our research, achieved the high object recognition rates by using CNN and also considering the position and the sizes of all the sensors. So in this research, we could use all the tactile information from the entire hand, but still it has a problem that the results are unstable because the size of the tactile feature is not uniquely determined by experimenter. Also, we also need to think like to recognize the softness and the slipperiness, I mean the object properties, so that the robot hand can manipulate a variety of objects. But when it comes to multi-fingered hand, occlusion usually happens, so we still need to focus on the tactile information. So here we propose the motion generating method based on graph convolution network, GCN, and also property labels. So firstly, we prepare the graph convolution network so that we don't need to do the engineering of the tactile information in advance. And also we prepare the property labels to input the GCN so that the hand can change the manipulation motion according to the property of the grasped object. So firstly, we did a comparison of GCN structure. So as you can see, most of the models could generate a successful motion. But actually, when it comes to the final posture of the manipulation, only this one, which has the most number of the convolution layers or the size of the convolution layers, could achieve the most number of successful manipulations. So we confirmed that the larger the number of the GCN convolution layers and the larger the sizes, we could get the greater number of successful manipulations. Also, when we confirmed the features from the convolution layer of model 1, which is the most successful one, we could confirm that the network acquired the feature of the position and the robotic configuration and the tactile features, like some middle finger, little index, and the palm. So we confirmed that it acquired a feature, and then it could generate a successful manipulation. Also, we did an experiment on the deformable object, and as you can see, it did a successful manipulation. But when we add the correct labels, like this object is a deformable object, and then the final posture is like this, it doesn't deform. But on the other hand, when we add the wrong labels to the GCN, it does the manipulation, but when we see the final posture, it squeezes the object. Also, when we see the trajectory during the in-hand manipulation, when we add the wrong labels to the GCN, it generates always generate the higher forces. On the other hand, the correct labels provided low forces, but still it could achieve the successful manipulation. So we confirm that using appropriate property level is effective, and in it, I mean, the hand didn't squeeze the deformable objects. So here's the conclusion. Thank you for listening.
Thank you. Then we have now time for questions. Let me just check the system. So I have the question. So you added a bunch of sensors. Did you also investigate like which of these sensors give you kind of the most information?
Yeah, that's a good question, and we didn't try it yet. But yeah, I want to try that. And also, I think the fingertip is the most important thing because the hand grabs the object from the desk, especially using fingertips.
Okay. So that's future work then.
Yeah, currently working on it.
All right. If there are no more questions, we will go to the next Spotlight talk. It's going to be Sarah Marullo from the University of Siena with the neck gripper, soft rigid gripper augmented with an electromagnet to precisely handle the gloves.
Hello everyone, I'm Sarah Marullo, and in this video we'll present MagGripper, a work on autonomous manipulation of garments. We propose to approach the autonomous garment manipulation by considering gripper and garment as cooperating parts of a dyad aimed to successfully achieve the desired manipulation. MagGripper allows to improve grasp repeatability and precision by design, compensating uncertainties in the target grasping locations. And the idea underlying MagGripper is currently patent pending. Garment manipulation is extremely challenging due to the fact that the configuration assumed by the garment is highly dependent on the grasping points, and the relatively small variations can lead to a task failure. On the contrary, grasping in proper locations lead to rapid and efficient task accomplishment. Our core idea is to exploit an attractive force between gripper and desired grasping points located on the garment. We consider to establish an attractive magnetic force between the gripper and the garment. Hence, we designed MagGripper, an augmented Zhou gripper embedding an electromagnet and capable of interacting with garments equipped with small ferromagnetic parts that can play the role of ornamental or brand elements such as buttons, studs, or small plates. MagGripper is an augmented Zhou gripper. In its central part there is an electromagnet mounted on the top of a linear actuator. By activating the electromagnet, a magnetic field is generated, which causes a magnetic force attracting the ferromagnetic part attached to the garment. Due to the attractive motion of the ferromagnetic part, a collision between the end effector and the garment occurs, and is detected by a small resistive force sensor located near the electromagnet. And the collision detection triggers the closing motion of the jaws. So the electromagnet allows to grasp the garment in the desired point, while the jaws allows a secure grasp maintenance during the manipulation. Concerning experiments, the electromagnet allows to grasp the garment without unnecessary wrinkles that usually lead to unpredictable change in the garment configuration. The electromagnet instead allows to achieve a conic-like shape, similar to a pinch grasp. Clearly, the larger is the plate located on the garment, the greater is the probability of successfully grasping the garment. At the same time, however, the probability of performing the grasp always in the same location decreases. Concerning weight and thickness of the garment, thickness is more relevant than the overall garment weight, As a matter of fact, changing the thickness results in varying the local mass the electromagnet has to attract. So, if the local mass increases, the electromagnet needs to be closer to the plate to cause the attractive motion of the ferromagnetic part. Having an attractive motion of the garment towards the gripper has interesting advantages. For instance, an intrinsically safer robot environment interaction, the possibility of performing aerial grasps, as well as the possibility of quickly re-establishing the contact in case of contact loss during manipulation, besides the possibility of coping with grasping point location uncertainties. Concerning the last point, we investigated the possibility of performing a sort of partially blind grasp. A blind grasp is meant to be a strategy according to which the robot is first commanded to reach the estimated grasping point, and if the contact between the object and the gripper is not detected, the robot starts spanning a small area around the estimated grasping point to exploit the magnetic attraction. To conclude, my gripper proved to be a suitable tool for autonomous grasping of garments, exploiting the magnetic force to perform a repeatable grasp execution and to compensate the planar uncertainties on the estimated pose of the target grasping point. Moreover, the extended point-like contact produced by the electromagnet allows to perform grasps without unnecessary wrinkles, achieving closing configurations more suitable to vision-based machine learning techniques for autonomous manipulation. And now we would like to establish a synergy with researchers in machine learning and producers of garments to develop new lines of robot-friendly garments. Thanks for listening.
Thank you very much. Just a reminder, you can use Slido or the chat to ask any questions to the Spotlight talker. I'm having a question regarding the need for the metallic plates in the clothing. You just presented that you might get it like in ornaments like buttons or so, but doesn't this restrict the grasping points too much? What do you think?
Well, we can have some small metal plates, but if needed, we can think about something more complex. We can also have some wires, ferromagnetic wires in the garments. So depending on what we need, we can think about suitable solutions. So if you need to grasp the object in a specific point, well, you can simply put a small plate in that point. The idea is that you are interested in grasping in specific locations. So if you know what are your locations, then you can exploit this information. Clearly, the specific location, in our vision, the specific locations are the output of some machine learning-based algorithm. So then we need a synergy between researchers and garment producers.
Okay, thank you. Very interesting.
Thank you.
And we continue the Spotlight talk with Minji Lee from Zhou National University with the work Interactive Real-Time Simulation of Robotics Snap Connection Process.
Hello, this is Minji Lee from Seoul National University. I will present about interactive real-time simulation of robotic snap connection process. Snap connection is a process connecting two objects into tight complementary geometry by exploiting deformation of deformable objects and is utilized in various industrial sites. For automation of these processes, simulation of the snap connection is necessary. However, the simulation is challenging for three reasons. Firstly, the snap connector has high stiffness and lightweight, which leads to large dynamics discretization error when any nonlinearity is included in the dynamics. In addition, to simulate fast snapping motion, a noticeably small damping is required, and for these reasons, the simulation becomes unstable. And finally, the deformable object has high dimension, which makes the simulation slow. Recent studies related to FEM simulations typically rely on iteration-based implicit Wheeler integration, which induces undesirable numerical damping and cannot simulate fast motions, whereas semi-implicit Wheeler integration is only conditionally stable. Also, in case of inversion-based simulations, model reduction is essential, and for this, a prior simulation or experiment is required. Therefore, existing simulators are inappropriate for snack connection simulation. In this paper, we developed real-time simulation framework of snack connection, which satisfies discrete time passivity. It does not require a priori simulation, and physical accuracy is validated with experiment. To achieve this, we approximated time-consuming complex collision detection process into simple MLP traversal and utilized GPU to enhance the simulation speed. As the position on the FEM surface is given as input, penetration depth is computed after traversing the network, and normal vector is calculated from the differentiated network. Also, we reduce the dimension of the dynamics of socket connector to speed up the simulation. Firstly, we segment the original linear FEM into one segment with contact and others without contact, and connect them via strong spring. Then balance model reduction is applied to each segment to further reduce the dimension. Balance model reduction is an analytical technique which does not require any simulation or experimental data. However, since coupling terms are still remaining, each equation cannot be solved separately. To circumvent the problem, we analytically eliminate the coupling terms via short complement. With contact force calculated from original FEM, we can solve dynamics of each segment in parallel. Also, every matrix used for calculation can be pre-calculated. This figure shows 3 different snack connectors, which are segmented into 2 segments. After segmenting and applying VMR, the dimension is reduced drastically. If nonlinearity is included in dynamics, discretization error is inevitable. Especially for high Young's modulus, it induces severe instability as shown in the figure. On the other hand, our framework satisfies discrete time passivity without any artificial damping while applying techniques to enhance speed. As a result, we can overcome the challenges mentioned above and stably simulate even with stiff material. Also, it can generate fast snapping motion as it can be simulated with small artificial damping. Additionally, it makes it able to use high spring coefficients to guarantee strong connectivity between segments and reduces discrepancy from the original problem. We validated the accuracy of our framework by comparing the reaction force with that of the experiment. As a result, RMS error of the force was 4.9 Newton, and the frequency has improved about 8.5 to 9.5 times from the baseline simulator. Also, we tested the framework with various geometries and material parameters, and it could robustly simulate different snack connectors. Thank you for watching.
Thank you very much. So I have a question regarding the simulator you use. Like, can you give an intuition how hard it is to set up this FM simulator to get useful data? You can hear me? Okay. Yeah, maybe you can just type. I'm going to read it out. The answer, like basically intuition about how difficult it is to set up a simulator, like the FM simulator, like how many parameters are there.
I think we may also move on and when the answer is available. So unfortunately, she has problem with the microphone, so I think we can move on, and when the answer is there, we just read it.
That's true. All right, then let's move on with Bruno Maric from the University of Zagreb. Will present soft robotic approach to autonomous plastering.
Dear ladies and gentlemen, my name is Bruno Maric from the Laboratory for Robotics and Intelligent Control System, LARIX. LARIX is a part of the Faculty of Electrical Engineering and Computing, FER, from the University of Zagreb. Together with my colleague Marcela Polic, we will do our best to present you our recent work called Soft Robotics Approach to Autonomous Plastering. This paper was submitted for ICRA 2021 workshop representing and manipulating deformable objects. In the beginning, please let me briefly introduce ourselves. Both of our research interests include soft robotics manipulation, with Marcela being more interested in tactile sensing, compliant control, and machine learning. On the other hand, my research focuses on compliant control of industrial manipulators and collaborative human-robot interaction in industrial environments. We are both involved as researchers in the Specularia project. If you are interested in our recent works, please visit our website and also please join Field Robotics 7th session of the conference, where Marcela will be presenting her paper called Compliant Plant Exploration for Agricultural Procedures with a Collaborative Robot. The presentation is organized as follows. In the beginning, I will introduce motivation and related work. Then we will talk about the shape modeling and control of the plastering knife. Since the estimation of the plastering knife deformation is essential for the autonomous plastering, I will introduce estimation techniques used in this work. At the end, experimental results and conclusion will follow. A motivation of this work was to develop an industrial soft robotic systems for the autonomous plastering of complex shaped surfaces. The main idea of such approach is a project Endorse, where we have successfully developed autonomous robotic system for grinding of complex shaped surfaces used in aircraft manufacturing industry. Our approach relies on deep learning-based soft body estimation, where the goal is to estimate shape and deformation of the flexible plastering knife. Controlling both the knife inclination angle and the contact force, the robotic system can apply different plastering strategies. For a proper execution of the plastering task, the robot needs to control both the knife inclination angle to the treated object and the contact force. Since the shape of the tool is a result of the contact between the plastering knife tool and the treated object, we have designed the control system that decouples the system into two parallel control systems by estimating the shape of the knife. The shape of the knife is estimated using RealSense RGBD camera, capturing the complete plastering knife. Inspired by the results from vision-based tactile sensing development, the plastering tool was enriched with visual clues for easy deformation modeling through image analysis. The knife shape was modeled using 3 deformation features. 3 features were later estimated using a deep learning model. During the training phase, a pre-trained architecture was used for deformation estimation on a custom dataset. The dataset was created through the experiment and data analysis. The approach presented here can easily be extended into a more complex 3D deformation modeling, where both the inclination angle and the torsion angle of the knife tool could be estimated. The evaluation of the proposed estimation method and control system is conducted through experiments using industrial manipulator KUKA KR10, equipped with sensors and specially designed plastering tool. The first experiment includes plastering task on a flat surface. On the other hand, second experiment is conducted on a piecewise flat surface with a single discontinuity between 2 flat surfaces. This is used to evaluate the dynamic response of the knife inclination control, resulting in knife inclination adjustment with low position change. In this work, deep learning is deployed in industrial tasks involving deformable object manipulation. A pre-trained convolutional neural network architecture is trained by a transfer learning paradigm. From the raw camera images, a neural network estimates the values of the deformation features of the flexible robot tool. The experimental results show that the provided control architecture ensures that the tip of the knife tracks the desired attack angle. The remaining information features, as well as the estimated contact force, will be used in the future work, where the approach will be extended with a coupled force position controller. For more information about our work, please take a look at our manuscript or contact us directly on our email addresses. Thank you for your attention.
Thank you very much.
Thanks a lot. I have a question. It's actually more a curiosity. So thanks for the talk, and the application is actually very interesting. I was wondering how the pre-trained architecture affected the performance of the approach. So have you also compared the results with learning from scratch?
Well, thank you for your question. I must admit that my colleague Marcela was completely involved in all parts about neural network. But as I know, the training using the pre-trained architecture was much faster.
Okay.
With the training from scratch, we will have much more cycles of learning, and the results will not be as good as we got with the one from pre-trained network.
Okay, thanks. I was wondering this because the ImageNet is composed of different samples from the ones that you need in your architecture. So that's why I had this question, but thanks a lot.
Thank you for the question.
All right, then we move on, if there are no further questions, to U5 Wang's presentation from Carnegie Mellon University, Learning Visible Connectivity Dynamics for Cloths Moving.
Hi everyone, my name is Xinyu, and today I will present our work in learning visible connectivity dynamics for cloth smoothing. This is joint work with Yufei Wang and David Held from CMU. Manipulating deformable objects have wide applications, from folding laundry to preparing food. However, these tasks are challenging for the following reasons. First, unlike a rigid object that can be represented by its 60 poles, deformable objects can have high dimensions state representation. Second, deformable objects can have infinite degrees of freedom, presenting complex dynamics. And third, due to heavy occlusion, it's hard to reason about the state of a cloth underneath its surface. So, given an image of the cloth here, how should we represent its state for manipulation? Previous method first maps an image to a latent vector, and then, combined with the action, learns a latent dynamics model that predicts the next latent state. However, such method does not apply any inducting bias and can overfit easily. Another approach directly learns the pixel dynamics model, but this approach also does not capture the physical structure of the cloth. In this work, we propose to learn a graph dynamics model. Given the observed point cloud, we first estimate the mesh of the cloth, and then learns a graph neural network dynamics that predicts the state of the cloth in the next time step. Why do we use a graph? The reason is that the cloth can be modeled by a set of points connected by springs. This gives a natural graph representation of the dynamics, and the forces applied to each particle can be modeled by different types of edges. For example, the forces applied to a particular particle include the gravity, spring force, and collision force, and these can be modeled separately. Here's an overview of our method, and I will describe each component in detail. In the first brain, given the RGBD observation, we first voxelize the point cloud and then compute the collision edges by connecting all points that are within the radius R to each other. For each collision edge, we learn an edge prediction GN to predict whether it is also a mesh edge. The input feature on the edge is the distance between the two endpoints. We then learn a dynamics GN. The input to the node feature include the particle position, its historic velocity, and an indicator of whether the particle is picked. The edge feature is the distance between the two endpoints. And the dynamics model then predicts acceleration for each node. Once we have the dynamics model, we play in a high-level pick-and-place action space to smooth the cloth. Given a pick point and a place point, we will first decompose them into a sequence of low-level actions, each denoting a small movement of the picked particle, and then roll out our dynamics model using these low-level actions. To plan with our dynamics model, we use a reward that computes a covered area in the top-down view of a set of spheres centered at each particle. And we greedily select the sample trajectories with the highest reward. Our dynamics model is trained in the Flex simulator wrapped in SoftG. The training data are generated from random pick and places, and the dynamics model is trained with a one-step dynamics loss. For smoothing the cloth, we use a normalized increase in covered area as an evaluation metric. And we compare other baselines that learn a pixel dynamics model, or a latent vector dynamics model, or directly learns an RGB-based policy. We first show that the estimated mesh edges are close to the ground truth at mesh edges. In simulation, our method, denoted by the blue line here, greatly outperforms all baselines on a different number of actions. Here, we show smoothing results in the real world with a Franca on. The left is a smoothing video from the robot view. On the top right, we show scores of sample actions predicted by VCD, and on the bottom right is a rollout prediction of the best action. We show results on two types of cloth. The first one here is a cotton cloth. The second cloth here is made of silk. We can see that in both cases, the robot is able to smooth the cloth in a few pick-and-place actions. In conclusion, we propose running a visible connectivity dynamics, which poses strong inductive bias that fits the physics of deformable objects like cloth. We show zero-shot sim-to-real transfer for cloth smoothing of different materials. For ablation studies and more videos, please check out our website and the paper. Thank you.
Thank you very much. Very nice presentation. There is some question from Slido. If you consider did you consider adding the action magnitude as a node attribute, or did you try different graph attributes that were not successful?
Sorry, there's a problem with my computer. Can you repeat the question?
Okay. Did you consider adding the action magnitude as a node attribute, or did you try different graph attributes in general that were not successful and then you went for this method?
Yeah, we didn't try actually our action representation is we didn't embed the action as a node feature, but for the pick point, we directly modify the graph structure that the pick point is rigidly attached to the gripper and its position and velocity is modified. So, and through that, it will through the mesh, the edge connections, it will affect the motion of the other particles. We didn't try with we didn't really try with many different combinations of the node features, and so yeah, I'm not sure how well they work.
Okay, there's a second question from David about how important was the edge prediction graph neural network to get accurate dynamics. Did you perform any ablation study?
Yeah, sure. We have different ablations where we removed edge prediction GNN at test time, but we only use the collision edges and we fix it through the rollout, and the performance is much worse. And one reason we guess is that the collision edges they are much denser than the mesh edges, and they are dynamically reconstructed at each time step, so they cannot represent the fixed underlying code structure, which affects the dynamics throughout a lot, and that leads to worse performance.
Thank you. Very interesting work. We move on with Peng Zhou from Hong Kong Polytechnic University with a latent and semantic framework for deformable object representation.
Hi everyone, I am Peng Zhou. I'm a PhD student at the Robotics and Machine Intelligence Lab at Hong Kong Polytechnic University in Hong Kong, China. In this video, we introduced a new data-driven latent and semantic framework for soft object manipulation. Soft objects are widely existing in our daily life. In the past few years, this domain has witnessed many encouraging results. For example, some works already can automatically control the curvature of the creature and contour of the soft objects, or bend or fold a tower, or even freely manipulate cables in real time. In spite of encouraging results from different soft object manipulation tasks, it is still very hard to extend the system for new soft objects, because they usually use different level of feature specific for different soft objects. So the objective of this work is to design a general representation framework to support different soft objects manipulation tasks. As shown in this figure, we built a 3-level representation framework, which can be partitioned into 4 layers. Layer 0 is to complete low-level geometric feature extraction, such as contour descriptor, surface normal, vector, and so on. Layer 1 and Layer 2 form the mid-level representation layers. The first phase is focused on dimensionality reduction to generate a latent space, and in order to have a concise and compact representation. In the second learning phase, we design several semantic techniques to better understand the latent variables. With the output from the mid-level, we design shape deformation analysis, which allow us to explore the high-level semantic shape knowledge. More importantly, shape planning from the current shape to the target shape can be achieved by geodesic path interpolation in the latent space. The left image shows the experimental setup of the shape data collection to build this framework, where a sponge bar labeled with 8 markers is manipulated by human hands, and then their positions are computed by motion capture system. The right figure shows 7 predefined shape classes. As for semantic deformation process, the left video shows the soft object manipulation by motion gestures, and the shape was represented as a point in the built latent space in a real-time manner. The entire deformation process will form a trajectory between different shape classes in this latent space, thus revealing some rules of shaping shape deformation in real-world applications. With this framework, we can solve a shape planning problem in latent space. Given current shape and target shape, we can form a shortest path in this latent space, and the geodesic path updated with a linear interpolated path. By reconstructing the geodesic path-based latent space shows a more smoothing and natural deformation process compared with the shortest path techniques. For more information about this work, you can visit our project website. That's all for my presentation, and thank you for listening.
Hello, everyone. My name is Zehan.
It's too early. Thank you very much for the presentation. I have a question regarding the type of deformable objects you use. You use this pool noodle. How would this approach kind of scale to more complicated or even more deformable objects like cloth or like t-shirts?
Thank you for this question. For more complex issue, I think if we can collect some data with a better strategy, we can still use this framework to solve some problems, especially for some visual planning. For example, when we try to close some t-shirts or some other garments, it's very important to have visual planning, since this task is kind of a long-term horizon task, right? And we also need some intermediate states that we can achieve the final goal one by one step by one step. Yeah, which is very necessary and also helpful for this kind of task. Yeah, thank you.
Thank you. Very impressive work. We move on with Sehang Weng from KTH, Royal Institute of Technology, and his presentation about graph-based task-specific prediction models for interactions between deformable and rigid objects.
My name is Zehan. Today, I will present our paper, Graph-Based Task-Specific Prediction Models for interactions between deformable and rigid objects. This paper has two contributions. First, we built a novel dataset for task-specific action effect prediction. Different from some previous work, we consider a bag with complex shape and multiple types of interactions. Second, we propose a method for predicting the interaction dynamics based on graph networks. Regarding the dataset, we generate 20 different scenarios by varying different task parameters. For each scenario, we split into 80, 10, and 10% for training, validation, and testing. These are examples of 4 different types of actions. To model the interaction dynamics, we start from what we have in the scene. In the scene, we have a deformable bag and multiple rigid balls. Each ball is represented as a key point, and the bag also has some associated connected key points on the surface. Each key point has a position, a radius, a fixed label flag, and a connection flag with other key points. For the radius here, when it is a ball key point, it is a ball radius. When it is a bag key point, it is a small constant value. The fixed label flag here is either 1 or 0. As shown in the opening case, the key points on the left handle is fixed in place, so the fixed label flag is 1, otherwise it is 0. The C flag here is either 1 or 0. It is 1 only when we assign connections between 2 key points. We also have some external input. We control one point and move it from one place to another place, which are P start and P end. We also have a radius variable here. When we control and move the ball, it is a ball radius, and when we control and move the back key point, the radius is set as a small constant value. We then convert the observations and the external input to get into a fully connected graph. We encode each key point as one graph node, including the position, the radius, and the fixed label flag. The spatial differences and the connection types are encoded as age attributes. The external input are encoded as a global feature vector. Given a graph at time step t, we want to predict the key point position at time step t plus h. Based on the graph representations, we propose a model with 2 different modules for capturing the dynamics, which are called APM and TPM. TPM is used to predict the movement of every key point, and APM is used to predict a binary mask, which indicates if the node is moved or not. In the inference stage, we have different inference models depending on how to use the modules. First, we build a one-stage model by using PPM alone. Then we build a 2-stage model by considering the APM module. APM produces a mask, and we only update the moved particles in the inference. Finally, we propose a mixed horizon strategy for long-term prediction based on 2-stage model. We train 2 different models for short and long horizon. In the inference stage, we combine 2 models to predict the final result. Here's the comparisons of 3 different inference models from vision inspection. The mixed horizon model fixes the sphere's point movement and has more accurate results compared to the original 2-stage model. Here we show one example of comparing the ground truth and our mixed horizon prediction model for pushing action. For quantitative evaluation, we first evaluate the single time step prediction error for the 1-stage and the 2-stage model. From left figure, we see that the 2-stage model decreases the mean position error and also reduces the inter-task variance. From the right figure, the model has similar performance on 2 different materials. We then calculate the long-term accumulation errors for different actions. The 2-stage model always outperforms the 1-stage model. The mixed horizon model reduces the long-term accumulation error, but sometimes produces worse result in short-term prediction. In conclusion, we built a novel dataset and show it is feasible to use graph networks to model interaction dynamics between rigid and deformable objects. The dataset and the code are publicly available. Finally, we would like to thank KAW, PR, ERC, and DFG for the support. Thanks for watching.
Thank you very much.
I think we have a question. So the question is, right, how to define the best number of graph nodes to represent different deformable objects?
So this is a good question. So the number of the nodes in the graph actually depends on the number of the objects, the rigid object, and also the number of the key point selection on the back surface. And in my paper, based on the dense mesh, we pre-select a sparse mesh on the surface to get a sparse key point set, and it is manually selected to preserve the overall appearance and the topology. And actually here we fix it, and we didn't test other set of selection for the key point, but it will be interesting to investigate in the future. Yeah.
Okay, thanks. And I have just a curiosity. So have you tried the models with even longer horizons? So it's really nice that you combine these models, but I was wondering how you selected the horizon for the long horizon model.
You mean to longer the prediction, the length of prediction, or use other horizons for the other horizons of the model? Okay, so in the because here in the data set collections, we fix the length of the data generation is 6 seconds. So in the inference stage, we only evaluate for the 6 seconds. And also regarding the mixed models, in the current settings, we choose a simple way to combine only 2 horizons, but of course we can use other more horizon models, as you said, and use other strategies to do the combinations or fuse them in a proper way. But here we do not examine this, but it will be very interesting to investigate, use more horizons and other strategies to do the fusion.
Okay, thanks. I think it's really, really a nice work.
Thank you.
There's one more question just coming in. If you are using model predictive control.
Yeah, so currently we do not use the predictive model for the control, but we are now going to incorporate the prediction model also with the MPC for the simulation environment, and it is ongoing, yeah, but not presented here.
Very nice. Thanks. This concludes the first Spotlight session.